this video, we're going to look at graphs of the potential energy function and find out what we can learn just by looking at the features of the graph. Let's restrict our discussion to a single object of mass m and one position coordinate x. We'll assume that the object is under the effects of a conservative force so that it has a potential energy function u of x. In other words, the potential energy only depends on its x coordinate. The potential energy graph depends on what type of force it is, but in this video we're just going to make some general conclusions. So let me draw a somewhat arbitrary potential energy graph. This blue line, again, represents the potential energy that the object would have at any given x coordinate. Let's consider the implications of conservation of energy to this graph. Based on our initial assumptions about what the system is, there's one type of energy for kinetic, 1/2 mv squared, and one energy for potential. These two energies are added together to get the total mechanical energy E, which is a constant. We understand then that v, the speed, and x, the position, can both change, but they must change together in a way that keeps the total energy constant. This equation lends itself to interpreting the energy as a horizontal line on this potential energy versus position curve. Let me show you why that is. In red, let's pick a certain value of the total energy E and draw across a horizontal dashed line. Notice that there are several places where this horizontal dashed line intersects the potential energy curve in blue. Let's mark those and discuss them a bit. At these intersection points, the total energy is equal to the potential energy at that location. Let's call this one on the left point A and give it an x-coordinate label of x sub A. Therefore, at this location, the total energy is equal to the potential energy. So there isn't any energy left over for kinetic, and we can conclude that at this location, the speed and kinetic energy of the object must be zero. At the other points that I've labeled on here, the intersections, the conclusion is exactly the same. These are locations where the velocity of the object must drop to zero because of conservation of energy. Note that if I had chosen a different value for the energy, say a somewhat lower amount, then these intersections with the potential energy curve would occur in different locations. So differing values of the energy as a horizontal line produce differing intersection points with the blue potential energy curve. We give these intersection points for a given energy a special name. They're called the turning points of the motion. The general definition of a turning point is a coordinate value at which the potential energy equals the total energy that the object has. A direct consequence of this, as we just explained, is that at a turning point, the speed of the object must be 0. Let's think about now what types of motion could exist for this object if it was under the influence of this potential energy function and having an energy level equal to, let's say, the red dotted line. We have 3 turning points here. 1, 2, 3. If the position of the object is between XA and XB, then its potential energy is less than its total, and it has some left over for kinetic energy. We can visualize the kinetic energy on this graph as the difference between the horizontal energy dashed line and the blue potential energy curve, right here. An object with an energy equal to the red dashed line would have a kinetic energy given by this distance. Therefore, whenever the blue curve is below the dashed line, the object is moving with some velocity. When the object reaches a turning point, its velocity momentarily becomes 0. And if the object was somehow imagined to be at a location beyond the turning points, we would find that no value of kinetic energy can satisfy the conservation of energy equation. Kinetic energy must be positive. So these points over here to the left of A and between B and C, these are called forbidden regions. Notice that if the total energy were to change, say from the red dashed line down to the orange dashed line, the forbidden regions would also change in size because the turning points move. So an object with energy equal to this red level could move back and forth between these 2 turning points, or it could move out here over to the right of location C, no problem. But it could not be found to the left of A or between B and C. If a different object with the same mass and same potential energy function had a total energy at the orange dotted line, that object would only be able to exist between this turning point and this turning point. I haven't given those letters, but between here and here would be allowed motion, and outside of there to the left, outside of there to the right would be totally forbidden.